Okay. So, so study survey sampling, and two books which you can refer for this topic, which I personally feel are good for problems. So one is sampling theory, and methods by S. Sampath, and the second is theory and methods of survey sampling by P. Mukhopadhyay. So the second book might not be available online. You can obviously buy this book, but this book is available in PDF, and this has many problems. So you can try solving problems from this book. But for theoretical parts, you can try to read the second book. But it is not necessary. But you can obviously, if you are curious, you can try reading this book. So okay. So basically, we will be talking about some notations and terminologies used in survey sampling. So first of all, we'll talk about something called a finite population. So till now, we generally talk about population as a huge countable set. Okay, so in this case of survey sampling, we mainly deal with finite population. Okay, so that is nothing but a set of finite number of a set of a finite number of, we say, distinguishable elements. So what do we mean by distinguishable elements? Basically, by distinguishable, we mean that we can number them as 1, 2, 3, and so on. So basically, say you have n persons, okay, so you don't know their identity at first, but obviously, if you number them as 1, 2, 3, and so on up to say capital N, you can then signify that number to that person. Okay, so that number basically identifies that person. So that is called a distinguishable element. So basically, for a population which is finite, you can identify each of its elements by a particular number, which I numbered them as 1, 2, 3 up to n. So it can be any other countable sequence. May not be always 1 to n. It might be a1, a2, a3 up to n also. So for simplicity, we talk about only 1, 2, 3 up to n. Okay, so and we generally consider the population size to be denoted by capital N. Okay, so all capital letters you see, they all signify population size or population entities. Fine. So now, generally, why do we do survey sampling? First of all, what is the motive behind survey sampling? The thing is that you are interested in studying a particular characteristic of the population. Say, suppose you are interested in studying the height of a certain set of individuals in a particular region. To gather all the data for all the persons living in that region, and you try to do some kind of data analysis with that data, right? So the thing is, in that region there might be millions of people residing, right? So you can't handle so much data at once. So that's why you need to draw a sample from that region so that it represents the population. Okay, so it should not be a bad sample which does not correspond to the population at all. That is, it is full of outliers and all. You don't need those type of samples. You need a sample which represents the population correctly. So that's the need of survey sampling, that you need to draw a sample in such a way that it signifies, or it more or less corresponds to your population of interest. So basically, we are interested in studying a particular characteristic say y, okay, of a group of individuals, and we only gather data only on this characteristic under study. Fine. So I will not bother about the redundant data, right? So I'm not bothered about where the person is living, or maybe what is its blood, what is his blood group, and so on. So for example, if I'm interested with his height, I will ask directly for his height. I'm not asking about his blood group or his address, right? So those type of redundancies we are neglecting. We are just interested in the particular characteristic which we are going to study. So that kind of data basically forms a representative sample. That is, that sample basically represents the study you would be conducting, and it also comes from the population of your interest, right? So this is the first step of survey sampling. So basically, we denote a sample, denote the population to be say y1, y2 up to say y capital N. Fine, this is my population. Note that all of them are denoted by capital letters. Y and N, both are capital letters. Fine. So now I define a quantity called a parameter. So what is a parameter? Look, in statistical inference, we have all learned what a parameter is. We basically learned that a parameter labels a particular distribution. For example, we might have learned about normal, say theta 1, these type of distributions where theta is called as a parameter, right? Because it is unknown, first of all. And if you know theta, you know the entire distribution. So these kind of quantities are called parameters. But in survey sampling perspective, any real valued function of the population entities of the population values, say the population mean capital Y bar, which is 1 by capital N summation yi running from 1 to capital N. Now look at Y bar. This thing depends only on the population values y1, y2 up to yn, right? It involves all the population values, and you're computing a function of these population values, right? So this thing is a parameter. Also, you can give another example, like you can consider the sample range, or sorry, the population range, y order capital N minus y order 1. That is the highest and the least values in the population. So these are also depending on the population entities. So this is also a parameter. Fine. So, so basically the goal here is the same. In inference, we all used to draw a sample from a population, construct a statistic so as to estimate this parameter theta, right? So in survey sampling, we'll do the same thing. We'll draw a sample from the population, construct a statistic, and now to estimate or to learn more about these parameters, say y bar or say s square, which is the sample standard deviation or sample variance, and so on. So we need to study these properties for the entire population, and we will draw samples again from the population and construct statistics. Fine. So the goal remains the same, only the notations vary, right? So the next Next thing would be
Okay.
doing. Till now, is it fine? Uh,
Yes, yes,
okay,
yes.
okay, okay.
Just that about the parameter, you said that
Yeah,
like earlier when we had distributions,
yeah,
so we had like two parameters that helped us to analyze the distribution. Like we had theta and sigma square.
yeah, yeah,
But here, if there is any function of the population
yeah.
values, then we say that it is a
It is a
parameter.
parameter. Yeah, yeah. So it
Okay.
is not. For example, in the example you are saying, say normal mu and sigma square. So mu and sigma square were necessary for you to determine the entire distribution, right? So for example, if you want to know the entire distribution of say a random variable x following this normal mu sigma square, you needed to know both mu and both sigma square, right? So that you can know the entire distribution of x. But it is not the case in case of survey sampling, because your first of all population is finite, and you can compute entities first of all from the population itself. So these things are known for you, okay, but you can't handle them because there is so much data. This n is so huge. So basically, so you draw a smaller sample from this population and try to guess what this y bar could be, okay. But it is not exactly the case in inference, because in inference there might be problems where you don't know mu. Okay, so you don't know the distribution at all. It might be the case, but it is not the case for survey sampling. You have the entire data at hand. You can compute, if you have a large supercomputer, you can compute the y bar, but generally you can't because there is too much data. So you will draw a smaller sample and compute statistics, okay, to guess about y bar. Fine.
Yes.
Okay. So so basically after this, we will denote sample. So what is a sample? Sample, as we all know, that it is a subset of the population. Okay. So there is a trick here. We denote sample to be a subset of the population. Say I am denoting the population to be capital S, and the subset is defined to be small s. Okay. So all small quantities denote subsets or samples, anything. And we call this sample size. There are various notations. You can use n of small s, or you can also use n. Anything we do. So the thing is, in normal set theory, what we mean by subset is that suppose you have a set, say A, which is 1, 2, 3, 4, 5, suppose. And by subsets, we mean, say, I take a subset B, which might be 1, 2, 3, or a subset C, which might be 2, 3, 5. Okay, so these are all subsets of A. But notice one fact, that in the subset, all the elements must be distinct, because that is the property of a set, that all the elements must be distinct within the set. But in survey sampling, this might not happen every time. Okay, so we will learn about some schemes like WOR or WR sampling, or with replacement or without replacement sampling, where the same element, say 111 might appear, or 112 might appear. So in strict mathematical sense, they are not subsets, because the same element is appearing thrice, or the same element is appearing twice. So this is redundant. This can't happen, right? So this is not a subset in the strict sense or the strict mathematical sense. So we loosely define this to be a multiset. So what is a multiset? A multiset allows you to include more than one observations of the same kind. Say one can be there many 4 times or 5 times. Two can be there 3 times. Any number of times you are allowing the entries. So generally, for survey sampling, we define a multiset for the population S, and we denote that sample size to be ns or small n. Okay. So is this part clear? We are not defining subset as that of in a mathematical sense, but we are defining that, as I said already, in a multi-set sense. Okay, that you can allow repetitions within the set. Okay, so this thing you need to keep in mind, that there might be repetitions within the subset. Okay. Okay, so now the goal remains the same. A sample is drawn to estimate the population parameters, and let's say the sample is small y1, small y2 up to small yn. Fine. Now, as we know in inference, any real valued function of these entities is called a statistic, right? So any real valued function of these, say, yi's is called a statistic. So we all know what a statistic is. Say we all denote this by tx or something. So this is nothing but sorry, ty in this case. Okay, so this is nothing but a real valued function of these sample values. So we just defined parameter, which was a real valued function of the population values, which were capital Y1 to capital Y, capital N. Okay, but since we don't have the entire population at hand, we are drawing a sample from the population. So the data at hand is your Y1 to Yn, small y. So the at most you can do is to construct statistics out of these data points y1 to yn and infer about the population data. Okay, so that is your main aim in service act. Fine. So is it clear till now?
Yes, this is clear.
Okay. Okay. So okay, so till now it's more or less analogous to your inference, right? So now here is a question that how can you choose such a sample? How to choose such a sample? By choosing a sample, I mean that, for example, there might be plenty of ways you can choose a particular subset out of a particular set, right? So, is there any particular rule by which we should choose a sample, or we just can choose samples haphazardly? So, this is a pertinent question in statistics. That suppose, okay, so let's see. Suppose you have a population which is given by the entire region here, so the circular region, say this is capital S, and your sample could be anything, any set within this capital S. Okay, so how can you choose? What should be your intuition to choose a sample out of this capital S? So what should be your basic instinct by which you can choose a particular number of elements from this capital S? Just you can just guess. There is no hard and fast rule.
I think the points that we choose as the sample,
Yeah.
they should not be like there should not be a pattern while
Okay.
we are
Okay. Okay. Yeah, that's perfectly fine. So you are some guessing some kind of a random nature, right, within the points.
yes,
So you are looking for randomness within the sample. Fine.
yes.
So okay. So great. So how can you ingrain the how can you build in randomness within a sample? What is the ingredient which ensures that there is randomness within the sample? Can you guess what can be present within the sample which ensures that it is random?
For randomness,
You are close. If you have guessed randomness right, then you can obviously guess this. What causes randomness within the sample? So you have heard of the of various probability distributions, right? So
yes,
if you assign a certain probability measure or a certain probability distribution over these, say, subsets of this capital S, then you can ensure some sort of a randomness within this capital S because you are assigning probability to this. So you don't have any prior idea that which sample you are going to choose, but you have assigned a certain probability to that, right? So assigning probability to the subsets of S, okay, so that ensures randomness. But you should also keep in mind that, yeah, this sort of thinking, which came to your mind first, this sort of sampling is called probability sampling. Okay, so you are always looking for randomness, right? Because why are you looking for randomness every time? Because you need a sample which is not biased, right? So that's why you're always looking for randomness, so that it doesn't feel that the observer who is drawing the sample is not handpicking any one of these entries, right? Because if he handpicks any one of these entries by his own will, then he is biased upon that unit, right? So it is necessary to include randomness within the sample first of all. So this is an entire whole new level of survey sampling called the probability sampling. There is also another sort of sampling called non-probability sampling, which does not assign any probability to the subsets. So it is kind of a deterministic approach. Say I have partitioned this set into, say, 4 parts, or more than 4 parts. Say I have partitioned this set into say 6 parts. Fine. So any observer might say that I will always choose the even number of parts. That is the parts which are labeled to be even. So 1, 2, 3, 4, 5, 6. So he always chooses this 2, 4, 6, these parts. Okay. So there is no harm in that. This is also a sample, but this is not random, because obviously you know that already he is biased on these three quantities, 2, 4, and 6. So he is not choosing anything out of 1, 3, or 5, right? So this is not random, and this type of sampling is called non-probability sampling, or this is also called a deterministic sample. Okay, so we are not interested in these type of sampling schemes, because obviously there is no probability involved, first of all. And also these type of sampling schemes are not basically studied in the literature, because basically they don't require statistics, right? You just know what samples will come in your hand, and so you basically manipulate the data in such a way that you get those samples. So there is nothing new in this, but we will study this probability sampling, which includes randomness within the sample. Okay. Okay, so now let's see. Okay, so we'll go
In
to,
the
yeah,
uh,
yeah,
probability sampling,
yeah.
like I did not understand. Like, are we matlab, like, do we know that the population is from a normal distribution or something like that, or are we just
No, no, no,
assigning?
no, 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 no. I'll just give an example so that it is clear. Okay, so first of all, the thing is that you have a set capital S. Okay, so this is your, say, the capital S set. And now, can you say how many subsets does this set have? Or all possible subsets of this set? Say I have the cardinality of this set to be, say, small n. That is, it has n number of elements. So what is the number of all possible subsets this set can have? Or as we say, what is the power set of S?
2 to the power n?
Yeah, yeah. It has 2 to the power n elements. Okay. So it can be fragmented into 2 to the power n parts. Okay. So
Yeah.
now my idea is to add probability. That is, I'll define a distribution P of S. Okay. So P of S over each such small s. Okay. So basically the idea is that that you are fragmenting the population into 2 to the power n parts, first of all. Okay, so there are many parts here, and you are assigning a probability distribution of selecting each part. Okay, for example, I can assign something like this, that, say, suppose my population has n elements. This is my population having n elements. Fine. And I am looking for subsets of size small n. Fine. So I'm always looking for a subset of size small n, or as I can say, this is a sample of size n. So I have a population of size capital N. I'm looking to draw a sample of size small n. Okay. And I say that without replacement, which will clarify later what it means actually without replacement. So basically, we know what without replacement means, right? Because we have already studied these type of topics earlier. So do you know what WR means or without replacement means? What type of scenario does this come up to? WR scheme?
If we are sampling without replacement,
Yeah.
I think that means that if we have once picked up one set, then we cannot pick it up again.
Yeah, perfect. So if you are drawing small n elements out of capital N elements, so in how many ways can you do this? How many possible samples are there?
We are picking up small
Small
n
n
element
elements from capital N elements without replacement. So how many possible samples are possible?
without
Yeah,
replacement. NCN ways.
yeah. Perfect. So you have NCN samples, right? NCN samples of size small n out of these capital N elements. If you do this without replacement. So what is your PS here in this case? So the PS in this case is 1 by NCN if my sample size is n and 0 otherwise. Okay, so now you can understand. Say you have a population of n elements and you are looking for subsets of size n. You are assigning equal probability of 1 by n choose n to each of these subsets, each of these n element subsets. Okay, so basically if you partition this population into say all n element subsets of this, so there will be n choose n such subsets. Okay, so for each such subset you are assigning equal probability of 1 by NCN. So that is your PS. So this is a probability distribution because this, if you sum all of these, this would be 1. It is a PMF, right? And it is also positive, so no doubt that this is a PMF. So you are assigning a probability distribution over subsets of your population, capital S, right? And this probability will help you judge, right, which sample to choose and with what probability. Okay, so now I think it's clear, right? So you are fragmenting the entire population into some samples, say of fixed size, say small n, and you are assigning certain probability of choosing each of these samples. Okay, it might not be always in chosen. This is only for the case of WR. This is for just instance that I'm just illustrating this WR case, but it can be anything. It can also be say I can assign a probability distribution like this, that P of S is say A1, A2 up to say N for n such samples such that summation AI is 1 or something. So you can assign any PMF to this. So not just only this 1 by n chosen, it can be anything. So you are just assigning a probability distribution. And by that distribution, you're drawing samples, right? So this is this clear now?
Um,
Yeah, you can say if you have any doubts. You
like
are dividing the entire population into say subsets of size n, okay, small n, because you're interested in drawing subsets of size n. Okay, so you have n chosen many samples within this population, and
yes.
you are drawing each such sample with equal probability, 1 by n chosen, right? So basically it is just drawing like from a uniform distribution almost. So if you fragment all these or if you fragment the population into these many entries or elements, and you are choosing randomly from each of these elements, so the probability of drawing any one of them is 1 by n chosen, because you have so many such samples. So this is one probability scheme. It there might be any other scheme as well. So this is just a distribution over the samples, over the number of samples, or the in the population basically. So
I
yeah,
like when we were studying with replacement and without
yeah,
replacement,
yeah,
matlab, ways of choosing a sample and counting basically.
yeah,
So like we had also studies that like if we are picking up, maybe there's a bag of balls and we are picking up
yeah,
balls from the bag, and we are doing it without replacement.
yeah,
So for the first time the probability is 1 by n, and then the probability becomes n
yeah.
minus 1.
Yeah. Oh, no, no, no. That is a different issue. I will address that issue after this. But the thing is that in this case, I'm not talking about drawing a particular sample. I'm talking about drawing all possible samples from this population. So all these fragments are samples. Okay. So they all satisfy the WOR rule, that once you take a sample or take an entry, any other entries will not be sorry, that entry will not appear in the sample again. So this is not the case. I'm just dividing the population. Here is your entire population, say. Okay, so I am dividing the population into NC and many parts. Okay, so there are always NC and many parts if you do WOR sampling, because there are all possible samples of size n is NCN, right? So you are dividing the entire population into NCN many samples. So this is your sample space, sort of. Okay, and you can draw any sample out of this, any sample. So you are assigning a rule that it does not matter which sample I choose. I will always choose a sample. Okay, and I am assigning equal probability to each such sample. So you can choose any sample of your choice from here, and that will be of equal probability. Okay, so this is not the WR scheme you are talking about is will encounter that in a later stage, but this is from the view of a sampling design. Okay, so this is basically viewing the sample as a part of the population. Okay, so basically you are dividing the
Mm.
population and you are choosing sample at random with equal probability.
So
So this
in
is,
this,
yeah,
it is not happening like we have picked up one subset from the
yeah, yeah, yeah.
NCN
If you pick up one subset, you are done basically, because you already have n element subset, right? So we are not digging into what is in the subset, since say for example I have 1 2 3, and I am looking for all two element subsets from this. Okay, so this is my population now. Yes. And what are the all possible two element subsets? This might be 1 2, this might be 1 3, and this might be 2 3 as well. Okay, so there are say three possible subsets. Okay, so what this WR rule does is that it assigns equal probability one third, one third, one third to each of these subsets. Fine. So basically, you are choosing 1 2 or 1 3 or 2 3, okay, with equal probability. So if you close your eyes and pick up any sample from this capital S, you might be ending up with either 1 2 or 1 3 or 2 3. This is the fact I'm telling. So I know what you are talking about. Okay, so that is at a later stage. That is within WR sampling scheme, that thing happens. But first of all, you have already defined the population to be this 1 2 1 3 and 2 3 by the WR scheme, that no two will recur again, right? So you already have the samples at hand, and you are assigning a rule how to choose these samples. Okay, so you are assigning an equal probability to all these samples, and any one of these can come at your hand. So this is an example of your sampling design. Okay, so this PS is called a sampling design. So suppose you didn't assign one third, one third, one third. Okay, so suppose you assigned say to 1 2, you assigned say 1/4, to 1 3 you assign say 1/4, and to 2/3, to sorry 2 3 you assign half. Okay, so obviously you can say that this thing is more likely to occur than these two, right? So this is also another probability rule which you can assign to these samples. So in that case, your PS will be different in this case. So there are a whole lot of sampling schemes you can talk about, or sampling designs you can talk about. So for WR, we generally talk about 1 by n choose n. That is, if you are talking about small n element subsets, you are talking about a probability of 1 by n choose n. Okay. Is it clear? We'll discuss the problem we mentioned about WR sampling after this. Okay. So is this whole idea of sampling design clear? That you
Yes,
are
it is.
you are choosing subsets by assigning a particular probability to them and nothing else. Okay.
Okay.
So this was the whole idea of sampling design. Great. So now, fine. So now let's move on to simple random sampling, which will be of prime importance for our purpose for ISI. So we'll go to simple random sampling, or as we all know, SRS. So what is my scheme here, or why is it called simple random sampling? First of all, so we are interested in selecting a sample of small n units out of a population of say capital N units, okay, such that there is a catch here that each unit has an equal chance of being chosen. So this is a criteria which is only characteristic to your simple random sampling schemes, is that this thing remains the same, that you're interested in choosing a sample of small n units out of a population of capital N units. Okay, but it has to be done in such a way that each unit has an equal chance of being chosen. Okay, so each unit should have an equal opportunity of being chosen within the sample. So this is a criteria which is only characteristic to simple random sampling. Okay, so basically it says that at any stage each unit will have equal probability of being chosen within the sample. Okay, so we'll discuss this. Basically this SRS has two parts, uh, which is your SRS WR and SRS WOR, right? So WR stands for with replacement, WR stands for without replacement. So what is done in SRS WR is that you choose or select small n units out of capital N units one by one, such that say at any stage each unit has equal chance of being selected. Okay, so basically this is quite simple. For example, say I have the set 1 2 3 4 5. So what SRSWR does, say I am interested in drawing only a sample of size 1 from this, okay? So suppose in the first draw, I draw say 2. Okay, so I draw 2. I then again replace it back to the sample. So again, my entire sample becomes, entire population becomes 1, 2, 3, 4, 5 again. So again, I draw say 3. So in my sample here, I have 2 and 3. And again, 3 is replaced back into the population. So again, I have 1, 2, 3, 4, 5. So at any stage, you are drawing out of capital N many elements. For here, for in this case, capital N is 5. So the probability of drawing any element is 1 by 5, which is equal, right? Because you are always replacing it back into the population. So it is implicit here that it is always having an equal chance of being selected every time, right? So that is the thing which is written here basically. So you are trying to choose n units out of capital N units one by one, such that at any stage each unit has equal chance of being selected. So each unit has 1 by 5 chance of being selected every time. Okay, so this is SRSWR. Is it clear? Uh, this is more or less,
Yes.
yeah. So the same thing now for SRSWR, the same thing will take place, but in this case, the elements will not be there. So basically, you'd be interested in selecting small n units out of capital N units, one by one, such that at any stage of selection, any one of the remaining, so here the remaining word is of prime importance, units have the same chance of selection. Okay, so as we are telling in the previous slide, that yeah, after say 1, 2, 3, 4, 5, suppose I choose 1. So now in this sample, in this population, we are left with 2, 3, 4, 5. Now it should happen that the probability of choosing 2, 3, 4, or 5 out of this sample or out of this population should be equal, right? So this is the idea of SRSWO. So even after deleting one entry, which has been included in your sample, the probability of choosing any one entry out of this 2, 3, 4, 5 will be equal again. So this is the idea of SRSW or nothing else. So just in case of WR, you are replacing it back into the population, but in this case, it is deleted forever, for example. So you are just taking it out of the population, right?
So,
Yeah,
like if we say of like if we have the population that is 1, 2, 3, 4, 5,
yeah,
and we are selecting a sample of size 1.
yeah,
So suppose first we are selecting 1. So the
yeah,
probability of selecting 1 is 1 by 5,
yeah,
because
yeah, yeah,
we are saying that they have the same chances of selection.
yeah, yeah,
And then, like since it is without replacement, so 1
yeah.
is not getting replaced into the population.
No,
So now if we are selecting 2, the
hmm.
probability should be 1 by 4.
No, no, no. That is the thing. Okay, so you are saying that after choosing one, you are left with 2, 3, 4, 5. Okay. So
Hmm.
the thing is, now it's almost intuitive that it appears to be that, yeah, the sample, if I choose any other sample from this 2, 3, 4, 5, it should appear with probability 1 by 4, right? But the thing is, that probability is conditional on the fact that you have chosen one in the first entry, right? So that is not a proper probability. That was your conditional probability, conditioned on the fact that your first draw was 1. This was your condition, that the first draw equal to 1. So if you condition this on the fact that your first draw was 1, that probability will not be 1/4. Okay. And the idea, then the irony is, even if it looks like it should be 1/4, the probability is still 1/5 for each entry, 1, 2, 3, 4, or 5. So we will prove this after this, that indeed, if you even delete one observation, say 1 or 2 or 3 after the first draw, the probability of choosing any other observation in any draw will again remain 1/5. Okay, so because of the conditional probability that your first draw landed you a 1 or anything, it could be anything. Okay, so we'll prove this. So that is the idea of your simple random sampling, because in simple random sampling, note that it does not matter if you do WR or WOR. Okay, each unit should have an equal chance of being chosen. Okay, so had it been your case that after choosing 1, okay, you are choosing 2, 3, 4, 5, then the probability of choosing 2 would have been 1/4. So it would have violated your condition of simple random sampling, right? So that should not be the case. So we will prove this, that it should again be 1/n. That is just an idea of conditional probability. Okay. So before that, I'll ask you to say for SRSWR. Okay. So we discussed about this PS, right? The sampling design. So the PS was your 1/NCN for your WR sampling. Sorry, WOR sampling. Okay. So this was your for WOR. So what should be the PS for WR? According to the same lines, what should be the PS of WR? If you draw a sample of size n out of, say, capital N population in units, just think along the same lines. What should be the probability? Note that you are assigning equal probability to all the samples. That is the main important thing.
With replacement also it should be 1/NCN.
No, because because in this case you are not allowing any repetition. Okay, so that's why you are choosing 1/NCN. But in this case, there might be repetitions. Okay, so what should be the denominator in this case? It should not be 1/NCN, because if you choose 1/NCN, you are already drawing up n many samples already. So that is not the case.
Oh, so
Yeah.
if we are saying with replacement, so
Yeah,
this
yeah,
means also with the like when you divided the whole of population into
yeah, yeah, yeah,
different subsets.
yeah, yeah.
Okay, so then choosing with replacement.
You are along the same lines. So basically, if you draw this thing, so basically you are again dividing the population into all n many subsets. Fine. So
Yes.
now in this case, you are replacing it back into the population again. Okay. So in this case, it should be 1/n to the power small n. Okay. Because if you think of this in this way, say not in the diagrammatic way, say I say 1, 2, 3, 4, 5.
Yes,
So yeah,
since we are choosing a sample that has small n elements,
yeah, yeah,
say suppose we have a population of 5 elements and we
yeah,
are
yeah,
choosing a sample of 3 elements.
yeah,
So for every element of the
yeah.
sample, we have
You
five
have five
options. So
choices.
that
Yeah,
is
perfect,
5 to the
perfect.
power 3.
Yeah, yeah. So that's why it's 1/n to the power n, where ns is small n and 0 otherwise. So this is your sampling design for your WR scheme. Okay, and that was your for your WR scheme. So perfect. So now let's move on to the main result, which I should discuss as we discussed in the previous slide as well. So it was that it is no surprise.
So when we do
Yeah.
simple random sampling,
Yeah.
do we have we selected the subsets from the WR scheme or the WR scheme?
Oh, it depends upon the sampler himself. So first of all, you need to choose a scheme and then you assign a probability distribution. Okay, so say suppose you need to draw a sample of size n. So the statistician now decides that I will go for WOR scheme. Okay, so if you go for WOR scheme, then you will need to do sampling via this sampling design of PS. Okay, and if you choose this scheme, you need to go by this. So this is the crux of the entire sampling scheme, that you need to choose either of the two designs or any other design as well. So these two are the standard designs.
Okay.
So basically, it is no surprise that the probability of drawing a unit, say UJ. I'm talking about a particular unit, say UJ, at any kth draw is 1 by capital N, okay, for SRSWR. So we already saw that we are already replacing it back into the population. So the probability of drawing any unit UJ at any draw is always 1 by N. So there is no trickery involved here, right? So the thing is that this is also true for SRSWOR. So the probability will not decrease in any way or increase in any way, right? So as far as we already seen that in the previous example, say 1, 2, 3, 4, 5, as long as we have chosen one, okay. Suppose in this case, our main issue was that, say I'm interested in drawing a sample of size 2 out of this 1, 2, 3, 4, 5 without replacement. So first we draw one, suppose, and now we are left with 2, 3, 4, 5. So anyone, basically anyone can have this intuition now that one is not in the sample. So 2, 3, 4, 5 will have equal probability. So equal probability meaning that all of them will have probability 1/4. So that is a wrong notion. Okay, so you are suppose drawing a sample of size 2, so you might draw anything out of this, right? So say you are drawing 1 and now you are drawing 3. So your sample contains 1 and 3. Fine. So this does not mean that 3 is coming with probability 1/4 and 1 is coming with probability 1/5. So this is a wrong notion. Why is it wrong? Because once you have taken out 3 from the sample, once you have taken out 1 from the sample, okay, in the next stage, this drawing of 3 is now conditional on the fact that 1 has been taken out. Okay, so it is now a conditional probability that given that 1 is out of the sample, I am drawing 3. So this is very different from drawing from 2, 3, 4, 5, only drawing 3. Because in that case, you are reducing the set 2, 3, 4, 5, and now you are drawing 3, so it should be 1/4. But it is not the case. It now depends on what sample you have taken from the first turn. Okay, so in the first turn, you have drawn 1. So it is now conditioned on the fact that 1 is out of the sample, you are drawing 3. So this is not 1/4. Okay, so that's why people have the wrong notion that, yeah, it should be 1/4. So it is not actually 1/4. Actually, it is again 1/5. So we will prove this, that it is again 1/5. Okay, so each element has equal probability of selection for SRSW. So let's prove this. It will be clear, I think. So we'll basically prove this thing that say selecting the probability of selecting any, say, UJ at any kth draw, this will be 1 by N. This is my goal. Okay, is it clear till now? if I prove this, then we'd be done, right? Because this is for WOR. Okay.
Okay.
So now the thing I will do is that I will define an event, say L. Okay. So that is the event says that a particular unit, say U of j, is not selected at the lth draw, suppose. So this is the event that the unit uj we are targeting, it is not selected at the lth draw. Okay. So now what should this turn out to be? What should be this event? That I am selecting uj at the kth draw, but al is the event that a particular unit uj, that is the unit uj, is not selected at any lth draw. Okay. So I can write this event as probability a1, that is, it is not selected in the first draw, intersection a2, it is not selected in the second draw, and so on. This goes on and on up to say ak minus 1, and then ak complement. Okay. Because why ak complement? Because it is selected in the kth draw, but in the first 1 to k minus draws, k minus 1 draws, it is not selected. So I'm taking intersection of those, but it is selected in the kth draw, so I'm taking a complement of that. Okay. So is this clear? Is this line clear? Why I'm writing this? Look, I am selecting uj at the kth draw. Fine. So this means since I'm doing WOR, it can't be selected in any other previous draws. Then it will not be in the sample itself, right? So this means that uj was not selected in the first draw, uj was not selected in the second draw, and this goes on and on. uj was not selected in the k minus 1th draw, but I have defined the event that uj is selected at kth draw. So this should be a ak complement, because in this case, in the kth draw, I am selecting uj. So this is the complement of ak. Okay.
Okay.
So now we use the same old trickery of conditional probability. So I can write this as probability of a1 times probability of a2 given a1 times probability of a3 given a1 and a2. So these are all standard notations, standard laws of probability. And this goes on and on up to say probability of ak minus 1 given say a1 to ak minus 2, and ultimately probability of ak complement given a1 to ak minus 1. Fine. So the entire thing I've just broken out into into the conditional probability events. Okay. So now let's go one by one. So what is the probability of a1? So what is a1? A1 is that this unit uj is not selected in the first draw. Okay.
That's true.
So in the first draw, what is the probability of not being selected? So the probability of being selected is 1 by capital N, right? So what is the probability of not being selected? So that is 1 minus 1 by capital N, right?
Yes.
Now, given A1, so given A1 meaning that it has not been selected in the first draw, what is the probability that it is also not selected in the second draw? So now in your sample, so now in your population, you have capital N minus 1 elements, right? Because one element has been selected, which is other than A1, other than uj. Okay, so what is the probability that uj will again not be selected in the second draw? Okay, so that probability should be 1 minus 1 by n minus 1, because you have now n minus 1 elements, and it is not again selected in the second draw, right? So that is 1 minus 1 by n minus 1. Fine. So this goes on and on again up to this term, which is 1 minus 1 by n minus this is k minus 2. So this is n minus k plus 2 after adjustments. And now, what are the number of samples remaining? So what are the number of elements remaining in the population? You have gone up to the k minus 2th step. So the number of samples remaining is n minus k plus 1, right? So now AK complement means that you are choosing uj out of the remaining elements. So that probability should be 1 by n minus k plus 1. Because in this case, you are choosing that element. So with equal probability, right? So that should be 1 by n minus k plus 1, that is the remaining elements. So, okay, so is this product clear, first of all? This is just you go sequentially. Okay, so is it clear?
Yes.
So basically, if you go up to k minus 2, you can see that this should boil down to n minus k plus 2. And after that, you are left with just n minus k plus 1 observations. So because already you have already taken out k minus 2 many observations, right? So you are left with n minus k plus 1 observations. So all of them have equal probability of selection. And in the kth stage you are selecting, so this should be 1 by this. So now if you if you simplify this, this should turn out to be n minus 1 by n minus 2 by n minus 1, and this goes on n minus k plus 1 by sorry, yeah, it's fine. So n minus k plus 2 times 1 by n minus k plus 1. So all these things cancel out. Okay, so you are just left with 1 by n. Okay, so this proves the fact that even if you are doing WR sampling, the probability of drawing any unit uj at any particular draw is always 1 by n. Okay, so you now can understand why this is 1 by n, because of these conditional probabilities involved.
In this proof,
Yeah.
we were already using we were assuming the fact that probability of selecting UJ at kth draw is 1 by n.
No. Basically, look, in probability of A1, okay, so in this case, look, in the first case, it's not a problem, right? Because all of them had equal probability of selection. Because look, in simple random scheme, first of all, you are assuming the distribution that, yeah, it's all of them have the equal probability of selection. So in the first draw, it is indeed 1 minus 1 by n, because this is just n choose 1 by capital N choose 1, right? So basically here small n is 1. So this is 1 minus 1 by n. So that's not an issue. But for the second case, you are now assuming that, yeah, A1 has not been taken into account. And now you are calculating the probability of A2. So I'm not assuming at any point that this should be 1 by n, because if I assume that, then there was no point of calculating the entire thing, right? So this is based on the fact that you have taken a particular sample out of the equation, and now what is the probability of getting getting this event, basically, that user is again not selected. So I'm not taking into account that it should be 1 by n. Rather, I'm taking into account that it is not selected, the complement event. Okay, so you can look into this proof. It is also in any standard book. You can look into this proof in, say, Sampath also. If you have any queries, you can ask me again. So, okay. Okay, so and for this reason, basically, we call SRS WR and WR both to be equiprobability sampling schemes. Okay, because the probability of drawing each element is 1 by n every time. So that's why. Okay, so I'll conclude this with one last question, which I'll ask you to think about, and then you can send me any, you can send in the group itself, in the Cheenta group, or you can also send via WhatsApp. Okay, so this question might clear your doubts basically. So suppose you have a bowl and say you have gems in them. Okay, so the usual pack of gems we all know, Cadbury gems. So now the thing is that all these gems are of different colors. Say blue, this is yellow, this is red. All these gems are of different colors, and no repetitions are allowed in these gems. Okay, so all gems are distinct and are of different colors. Say I have capital N gems, all of different colors. Fine. So now I have two players, say A and B. Now, say player A closes his eyes and grabs 5 gems all at a time. Okay. And player B picks 1 gem at a time 5 times. Okay, so these are apparently two different schemes of drawing 5 gems. So I'm interested in drawing 5 gems from this entire population, and two observers A and B. They one of them is grabbing 5 gems all at a time by dipping his hand into the bowl, and the other observer is picking 1 gem at a time 5 times. Okay, by each time by closing his eyes and randomly. Okay, so assuming randomness. So now these two seem to be different sampling schemes. So now suppose both of them land up with the same collection of gems. Say both of them have the same collection of gems, say white, yellow, blue, orange, red, and say green. Okay, so both of them land up with the same collection of gems. Okay, so maybe A might have got blue first, orange second, red third. B might have got Y first, green second, and so on. So the ordering does not matter. Okay, in anyhow, they have picked up 5 samples, and both their samples correspond to each other. Okay, so both the samples are equivalent for both the observers. Okay, so now under these two schemes, will this event have the same probability? Or in other words, we can say that are these two schemes the same or they are different basically. So the thing is that it appears now that there are two different schemes, and you have got the same sample out of these two different schemes. Okay, so is the probability of getting this sample for both these schemes the same or they are different? Which also answers the question, is that these two schemes the same or are they different? Okay, so basically it will take some time to think. So basically you can think and let me know any day by this week. Okay, so if you have any answer to this, I'll be more or less uh, happy to hear your solution. Okay, so try to think about this problem, that whether this sample will have the same probability in both scheme 1 and scheme 2. Okay.
Okay.
Okay, so uh, will you be joining the next class with the senior batch maybe? the platinum course, as far as Srijit told. So if you join the class, then we'll be doing basically estimation and all mean estimation and confidence intervals for survey sampling techniques and all. So before this, we already covered this part in yesterday's class. So the same question was posed to all the students. So if you come up with any unique solution, you can definitely post in the group, or you can send me in WhatsApp as well. No problem. So try this problem and let me know. Okay.
Okay, so we'll be having class today at 7 p.m.
Okay. So today I think Srijit will take the class, right? Today is Thursday. So I think either Srijit or Uttaram. I think Srijit will take the class, as far as I know. So today might be not a sample survey class for Srijit. So it might be any probability theory class, I presume. So uh, basically, I take classes on Wednesday from 7 basically. So and the next 3 weeks will be dedicated to survey sampling itself, and after that we'll go to regression and all. And there are two separate batches for Srijit and Uttaran as well. So Srijit will teach, I think, probability theory, and Uttaran will teach linear algebra real analysis, as far as I know. So mm, basically, there are three classes simultaneously going on Friday, Thursday, and also Wednesday.
Okay, so we'll have classes 3 days a week.
I don't know whether the Friday class is applicable to you, because it is for the juniors basically for real analysis. But I think you need to do two classes, the Wednesday one and Thursday one, I hope. So
Okay.
you can talk to Srijit about this because he knows the entire schedule. So that would be
Yes,
helpful.
because he also told me about only two instructors, you and himself. So
Oh, okay, okay. So then you are for the senior course, right? So you read in third year, right? You're opting for ISI instead.
yes.
Oh, okay. So then I don't think you will need the Friday class. You will just need the Wednesday and Thursday classes. So then it's fine.
Okay. And like these classes are just the revision classes.
Yeah, yeah.
So
I'm teaching survey sampling now, since it was not in JAM. So we are starting with survey sampling just from yesterday, and we'll be doing survey sampling for say 3 weeks from now. And after that, we'll go to those topics which were not covered in IIT JAM, right? So there was ANOVA, there was design of experiments,
yes.
analysis of regression, and so on. So only those parts which are appropriate for examinations will cover. Okay, so
So
uh,
like ANOVA regression, like we'll have
yeah, yeah,
only
yeah.
revision classes or we'll be
No,
covering
no,
the
no. We are,
syllabus.
no, no, no. There are no revision classes. Basically, we are teaching this for the first time now, because till now there has been no ANOVA classes because of JAM and all on all examinations, because they don't include ANOVA in these topics. So these will be just rigorous classes, theory classes, and also problem solving, both.
Okay. And like you told about real analysis and everything. So like
Real
if I have
analysis classes will be revision classes by now, because you can have access to the lectures from the previous classes, because they, I think, have been uploaded in the Cheenta website or the Cheenta YouTube channel. And this at this time of the year, basically all classes are revision classes for real and linear. Okay. Uh, I think for linear, some part of theory is left regarding eigenvalues, eigenvectors. Otherwise, it is theory. It is revision, basically. So,
okay.
okay. So you can try this problem. And if you have more doubts, you can let me know in WhatsApp. Okay. So I need to end this here because we are already past time. Okay. So
Okay.
you can let me know, and you can also solve this problem and let me know.
Okay. So
Okay.
if I
Yeah.
like if I join the class and hello.
Yeah. Yeah. Yeah.
if I join the class and if I have any doubts, like other than the revision classes or the study classes, can I join with the mentor and like
Yeah,
discuss
yeah,
the
yeah,
problem?
yeah. There is no problem with that. Already, I think Srijit has mentioned this. You can obviously share your doubts with any one of the mentors. There is no problem in that. Okay.
Okay, okay.
Okay. So uh, I'm ending this here, right? So
Thank you so much.
yeah.